Hello, in this video I want to show you how to create a rainfall runoff model over a small catchment with a stream in GIFMod. So this is the diagram that you see is basically our conceptual model. So we're gonna assume a kind of 100 meters by 100 meter catchment that is basically that contributes into a stream. So this video is going to have two parts. In the part one, what I'm going to do is that I will just assume that the catchment is completely impervious. So you can imagine, I don't know, a parking lot with no infiltration that discharges into a kind of an urban stream. Uh, then in part two, what I'm going to do is that I will add the soil layer and a groundwater layer, and I will allow infiltration to happen. And also I will basically somehow connect the soil and the groundwater to the stream so that we can also model interflow and base flow and things of that nature. So so basically, so this is a very simple model. Of course, you can basically expand this later on. You can have it maybe, I don't know, several subcatchments contributing into a stream network just by expanding what I'm going to show you right now. So on the diagram you see that I've basically, this is completely superficial, by the way. I just made up the example. I came up with some elevations. So let's say, for example, the centroid elevation of the catchment, surface of the catchment is 125 meters from sea level or any other datum. And then I'm gonna assume that the bottom elevation of the stream is 120 meters. And then what I'm gonna do is that I will uh, just as for my basically downstream boundary condition, I'm gonna uh, assume another stream segment. But then what I'm gonna do is that I will set some parameters for this stream segment so that it doesn't, basically the hydraulic head doesn't change as a result of the flow into it. So the storage of this element will change, but the hydraulic head will not change. So you can think of this as, let's say there's a bigger stream or river that our urban stream kind of pours into, and as a result of the flow from our stream, the elevation of the water in the receiving water does not change. And then we have some elevations for example, groundwater table that I'm going to talk about in part two of this video. So let's get started. So what I'm going to do is, the first thing is, let's add our catchment. By the way, what I'm going to do is that I will run the model at different stages. The results, of course, doesn't make sense because if our model is not complete, but it gives us some idea about what's going on how things work and so on. So I thought that those may be beneficial to results to see. So this is our catchment. So let's set some of the properties of the catchment. So as we see in this image, it's basically the length and the width of the catchment is 100 meters each. So therefore the area will be 10,000 square meters. The bottom elevation is basically the bottom elevation of the centroid, which here we said it's 125 meters. So I'm gonna just enter 125 meters. We're gonna need some additional parameters that are not specified in this diagram. For example, we need the Manning roughness coefficient of the surface of the catchment, and also the Manning roughness coefficient of the stream. And then when we get to part two and we talk about the soil, we're going to need some soil parameters as well, including saturated hydraulic conductivity and soil retention parameters and so on. So anyways, let's just keep on going with this. Okay, so that's pretty much all we need for our catchment. Now, just something to point out, there are some parameters that we could specify for our catchment, but I'm going to avoid that. Specifically, there's this Manning roughness coefficient that we could specify, and the width and the length. And these things, I'm not going to specify them here. The reason why these parameters are provided for a catchment is essentially if I want to create a grid of a catchment, for example, to create a distributed model, then if I assign them assign these values here, then when I create the grid, they will be automatically assigned to the connectors connecting these, segments of or elements of the catchment. But then in this example, what I'm going to do is that I will assign the width, the length, and the Manning roughness coefficient to the connector that will connect the catchment to, let's say, the stream later on, right? So this is all we need for our catchment at this time. What I'm going to do now is I want to apply some precipitation to the catchment, and then I'll see what happens. So in order to do that, what I have is that I have this precipitation data that I kind of created for another project. It's actual precipitation data recorded at the Baltimore Washington Airport during year 2012. So basically what I'm going to do is that I just go to climate setting, I click on the value box in front of precipitation, and then I know where I've saved this file that I was just this precipitation file. So it's actually should be right here. So it's called the file is called rainreal.txt. I'm going to go and open this text file later on to show you what the structure of the precipitation data should look like. But then this is it. So I can open it and I can look at how it looks like by basically right clicking on this address to the file, and then clicking on the flow. And here is how the precipitation data looks like. As you can see, it's from January 1st, 2012 to the end of 2012. So now if you want to look at how the precipitation file look like, we can basically just open it with a text editor. So basically it's here, right there, and as you can see, this is kind of CSV data, and like a comma separated Excel file, and it has 3 columns. Okay, so the first column is the start of a precipitation bin, if you want to call it that way, and then the second column is the end of that bin, and then the value in the third column is essentially how much precipitation occurred during that time interval in SI units, in meters essentially, right? And these values, the value you see here, 40,909 and something, that's actually a date. So if you copy paste this file into Excel and then change the format to date, you're gonna see that this number is maybe 1 a.m. of January 1st, 2012 or something like that. Okay. Okay, let's move on. Now, basically, okay, next thing I need to do is to change the simulation period to be consistent with my precipitation data. So in order to do that, I go to project settings, simulation start date, and then I change this to 2012 January 1st. Okay, so that's going to be my simulation start time. And then simulation end time will be, let's make it 2013 January 1st. Okay. So now I can actually run the model at this stage to see how things look like. So let me just save this. I'm going to save it as Rainfall-Runoff. Okay. Now let's just run it. It's very simple. Okay, so we're done with the simulation, and now what we can do is essentially we have a catchment that doesn't pour into anywhere else, so we don't allow any water to go out of our catchment. So what we expect is, and then there's no evapotranspiration, there's no infiltration, so we expect water to just accumulate over our catchment, right? So if I look at, for example, water depth, here's what I'm going to see. The water depth just keeps increasing, and it gets to around 1 meter, and that's the typical amount of precipitation, yearly precipitation in DC, Baltimore area, right? So So this makes sense. So now we go to the next stage, and we're gonna add our stream segment. Okay. In order to add the stream segment, I'm gonna just click on this icon to add a stream segment. So let's just reshape these things so to match our conceptual model maybe. Okay, so this is our stream. The stream is okay. Let me go back to the diagram. By the way, I can just minimize this window. Okay, so this is our stream is the length of our stream is essentially 100 meters, as you can see in this diagram. And then the width of the stream, I'm going to assume, is 1 meter. But I don't have to specify the width of the stream for the same reason that I mentioned for the catchment. So anyways, the area of the stream segment is going to be 1 meter width multiplied by 1,000 meters length. So this is going to be 100. The bottom elevation, we decided to make it 120 meters. Okay, so this is going to be bottom elevation of 120 meters. And then I'm not gonna specify anything else. That's all we need. I'm not specifying the Manning roughness coefficient because I'm going to later on assign the Manning roughness coefficient to the connector, connecting my this upstream segment, let's call it upstream segment, to the downstream segment, which is going to be our boundary condition essentially. So that's all we need for the stream. Now next thing what I'm gonna do is that I will connect my catchment to the stream. Okay, so we have this connector. So let's now assign some parameters to this connector. So let's say the Manning roughness coefficient. I mean, typically the Manning roughness coefficient of sheet flow is quite high. So I'm going to just say, let's say 0.1. Okay, so that's the Manning roughness coefficient. We need a width. That's the width of the flow, right? So if you look at this diagram, you see the width of the flow, the sheet flow, is going to be 100 meters, right? So that's what I'm going to do. And we are also going to need a length. Okay, so the length essentially is the length of the connector. So the connector connects from the centroid of the catchment to the centroid of the stream. So that's going to be 50 meters over the catchment and then 0.5 meters over the stream. So this length is going to be 50.5. Now it doesn't really matter that the 0.5 of the stream really shouldn't matter. I mean, you can use your own judgment and say, we consider water flowing into the stream at the edge of the stream is basically that's when the flow ends. So you can say 50 and the results should not be affected that much by that. So but I'm going to use 50.5 and that's it. So now we got this model of a catchment that pours into a stream, and but then the water does not flow from the stream anywhere. So what I expect is if I run this model, I'm going to have a little bit of water flowing from catchment to the stream, and then it's going to stop there, and then the system will be flooded. So let's just try it. Okay, so I'm going to run the model again. It's going to take a little longer. Oops. Okay, so this is what happened. So this is there's a limit. There's a limit that is set on the number of times that the matrix is basically the inverse of the matrix is calculated in the computation. We call out those epochs, right? So there's a limit on the number of epochs, which is 20,000. And this time it happened that the model required more than that. So basically it as soon as the simulation reaches a number of matrix inversions more than the limit that is set, it basically stops. In order to avoid that, what we need is that we need to increase this number, the limit on the number of matrix inversions. So what the way to do that is I just go to solver settings, and then there's this property called maximum number of matrix inversions allowed, and I just change it to I increase it by tenfold. So now it's 200,000. And I try to run the model again. let's just wait until the simulation ends. Okay, now it's done. Now let's look at the results. So the first thing I want to look at is, let's look at the flow going from the catchment to the stream, right? So I'm going to right click on this link and then I'm going to plot flow. Okay, so this is the graph that I see. So what you see is essentially you have some flow at the beginning and then you have no flow going forward. So what happened is at the beginning you have the hydraulic head of the catchment is higher than the stream, so you have some flow from the catchment to the stream. But after some time, the hydraulic head of the both catchment and the stream becomes the same. And since precipitation is happening both on the catchment and the stream, their hydraulic head will keep rising at the same rate. So there will be no flow from one to another one. I can verify that by, maybe I can look at the hydraulic head over the catchment. So let's plot head here. And then I can also look at the hydraulic head of the stream. And then I can somehow compare them. So basically if I copy this, the hydraulic head of the stream, onto this graph showing the hydraulic head of the catchment, this is what I'm going to say. So initially there's a difference, but then they become equal and they keep on going at the same rate, right? And therefore there will be no flow, right? Okay, next stage, what we're going to do is that we're going to add this boundary condition, right? So the boundary condition, what I'm going to do is, if you look at this diagram, it says, there's this, this elevation. What I meant by that was I want to fix the hydraulic head of this downstream catchment to be 120 meters, right? The same as the bottom elevation of our upstream stream segment, right? So and that's so that's why we're not going to need a lot of information about this basically lower or dummy stream segment, because we're not actually doing a we're doing a water balance on it, but we're not calculating the head, and we're not calculating the flow based on the dynamic head here. So I'm going to show you how to do that. So basically what I'm going to do is that I will add another stream segment. By the way, this doesn't have to be a stream, it can be any other block, because all we want to do is that we want to fix the head. So basically I'm going to add this stream 2. And then the bottom area actually doesn't matter. It shouldn't. GIFMod does not allow a bottom area of 0. But other than that, we can put any number we want. And the bottom elevation also does. I'm gonna put something reasonable. So let's say 118, right? So 2 meters below the head. 2 meters may be too much, but let's say 119. It doesn't really matter. Then next thing is, there is this property called head storage relationship, right? So head storage relationship, and here actually I can type an expression, an actual equation, but in this case what I want to do is that I want my head to be fixed, so I'm going to make it 120 fixed. And that's pretty much it. Now the last thing is I want to connect my stream here, this upstream segment to the low stream segment, and then I'm going to assign some properties to this connector. So the Manning roughness coefficient, let's say, maybe 0.011 would be a reasonable Manning roughness coefficient for a channel. And then we also need to provide the width, and I mentioned that the width, let's just assume it's 1 meter, so I'm going to type 1 meter here. And then the length is, I don't know, it's just kind of depends on our judgment again. But what I'm going to assume is that let's say this downstream element is just similar to the upstream element, so they're both 100 meters long, and therefore the length of this connector connecting the centroid of the upstream segment and the low stream segment is 100 meters. Okay, I think that's pretty much all we need. Okay, I'm going to save the model here, and I'm going to run it. Okay, done. Now we can look at the results. So let's say first let's look at the flow going from the catchment to the stream. So I'm going to plot this. So this is our flow. Okay. So you get something around, you know, the peak, something around, I don't know, maybe 6,500 cubic meters a day and so on. We can look at the flow going from the upstream, from basically the flow going out of our system. Okay, so that's what we have. And we can look at the water head in the stream. So let's, or maybe water depth. So you can see that, you know, the stream, as we expect, sometimes gets dried. And that's what is expected. This is a small stream. And, you know, completely pervious surface, impervious catchment. So the water depth gets to, I don't know, 0.06 sometimes. We can look at how much the total flow that went out of our system by looking at the storage of this dummy block. Okay, so we see around 10,000 cubic meters, and that's what is expected. And that's pretty much it. And so next, look for my next video, which is going to be basically the continuation of this work. Basically what I'm going to add is I'm going to add infiltration and groundwater to this simple model. Thank you for watching.